Hi everyone, I am Crew Amos, a student of USTED. Today I'm going to lecture you on robot construction, designing stable structures. You have heard about a robot, some people don't even know how a robot looks like. I'll show you the picture of a robot. You'll see how it looks like. Well structured one, the stable one. Let's see. You see? Yes. So this is a picture of a robot. This well structured, it is stable. You can see it can stand on its own without falling because it is well structured, has the ability to stand, has the stability. Yes, that is why it can stand on its own. So we will teach you, we will guide you on how to construct the same thing. So that when you send your robot, go and buy me perfume. The robot will not go and fall in the gutter. Yes. Okay, so let's go. Before that, introduction to stability. What makes structures stable? Have you ever tried balancing a pencil on your finger or sticking several books without them falling? Some objects stay upright easily, while others tip over with the slightest touch. Understanding why this happens is the foundation of building strong, stable robots. The key question is, why can a pyramid stand firm for thousands of years while a tall tower might lean or collapse? Why so? And then the answer lies in three important concepts. That is the mass, how much stuff an object contains, and then we have the center of gravity, the point where all the weight is evenly balanced. Then we have the base of support, the area beneath an object that keeps it from falling. Understanding mass and weight. Mass is the amount of matter in an object. It stays in the same regardless of where the object is, measured in kilogram or grams. Weight is the force caused by gravity pulling on mass. It changes depending on gravity. You weigh less or on the moon. Mass, and it is measured, weight is measured in Newton. Okay, so a robot with too much mass in the wrong place will be unstable. The distribution of mass affects how easily a robot tips over. Heavier parts should generally be placed lower in center of gravity. The center of gravity is the point in an object where its mass is evenly balanced in all directions. It is a balancing point. That is it. It is a balancing point. Visual examples. Object of gravity location. The ruler middle of the ruler. Yes, ruler. So when you take a ruler, the middle of the ruler becomes the center of the gravity. Then you have a baseball bat closer to the thicker end. That is where the center of gravity is located. You have a pyramid low and centered. A person standing around the hips. A rule of stability. A structure is stable when its center of gravity stays within the base of support. If center of gravity is inside the base, structure is stable. If center of gravity shifts outside the base, structure tips over. That is it. Tip troop walker example. Tip troop walker uses a long, this one is very great. He uses a long pole to lower their center of gravity, widen their base of support, allows more adjustment to keep center of gravity over the rope. External forces affecting structures. Robots and structures must withstand various forces. Forces effect on structures. Example: weight push downwards comprising materials. A robot carrying a heavy load when pushes sideways can cause tipping tall robot outdoors. Motion or acceleration create inertia inertial forces, robots moving fast then stopping suddenly. And the impact, sudden force from collision, robot bumping into the object, vibration, repeated shaking can loosen joint robot operating on rough terrain. How rigid bodies respond to forces. Forces type what it does. Example: tension pulling or stretching forces a rope being pulled. Compression pushing, squeezing force a column supporting weight. Torsion, twisting force a screw being turned. Shear sliding forces scissors cutting paper. Principles of stable structures. What makes a structure stable and strong? Factors it can help. Wide base increase the base of support, making tipping harder. Lower center of gravity keeps the balancing point closer to the ground. Even weight distribution prevents one inside from being too heavy. Strong joint prevent parts from separating under stress. Triangular shapes distribute forces efficiently. Tension and compression work together. Reinforcement adding support or raises strengthen weak points. So, when you are building a robot, let's consider these principles. Yes, robot-based design. When building a robot, consider the following: one, keep heavy components low. Keep batteries, motors, and heavy materials near the bottom. This lowers the center of gravity. Make the base wide. Make the base wide. A wider base, more stability. Think of a triangle or rectangle base shape. Distribute weight evenly. Don't place all weight on one side. Balance the robot left to right, front to back. Use counterweight if needed. Add weight on the opposite side to balance heavy components like crane using a heavy base to prevent tipping. Reinforce reinforcements. Use strong connections, glues, screws, brackets. Weak joints can cause collapse under load. That is it. We have GS and mechanical systems. How GS helps robot. GS controls speed, how fast a robot moves. Torque, how much turning force the robot has. Direction, which way parts move. Timing, when movement happens. Types of GS. GS type purposes. Beef GS transfer motion between shaft at angles to bracket 90 degrees Celsius. Some gears achieve high torque and speed reduction prevent reverse motion. Spur gears transfer motion between parallel shafts. Rack and pinion convert rotational motion to near motion. Let's look at real world applications. Very low center of gravity, but parts are close to ground. Wide wheelbase for better stability in corners. Heavy engine position low and centered. Example: gantry cranes, heavy counterweights at the back, wide stable base to prevent tipping. Load is carried close to the support structure. Boarding and sky crafts claspers, deep foundation, heavy material at the bottom, triangular balancing in the framework, designed to withstand an earthquake. Okay, so in summary, mass is the amount of matter. Weight is the force of gravity on mass. The center of gravity is the balancing point where mass is evenly distributed. A structure is stable when its center of gravity stays within its base of support. External forces, wind, weight, motion, impact affect stability. Rigid bodies respond to tension, comp- compression, torsion, and shear forces. To make stable robot, keep the center of gravity low, make the base wide, distribute weight evenly, use strong joint and reinforcement, consider counterweight when needed. So, questions for review. What is the difference between mass and weight? Why is it important to keep the center of gravity low in a robot? If your robot keep tipping over when carrying a load, what changes could you make to improve it? How does a tightrope walker stay balanced? What forces act on a robot when it moves quickly, then stops suddenly? Why a triangular shape often used in the strong structures? What is the relationship between the base of support and the center of gravity? Name three ways to make a robot more stable. So here ends our lecture. Thank you all for your participation. Yours, thank you.